So this is EE 619, lecture 18. So I want to do a quick recap of what we have seen so far. We said that the absolute delay of any gate can be written as a unitless delay into the delay of the inverter. Then this unitless delay is parasitic delay plus the stage effort F, where the stage effort is the logical effort into H. H is the electrical effort. So now H, or the electrical effort, is also called as the fan out, right? So this is equal to C out, the total load capacitance seen by the device that you are interested in, divided by the C in of the device that you are working with. Now, this definition is slightly different from another definition that is also commonly used for fan out, which is simply the number of gates that are driven by the design that you're looking at. So for example, let's say I have this inverter and I'm interested in looking at the fan out of this inverter. Let's say this is driving another inverter, maybe an AND 2 and, sorry, not 2 and an AND 2. Our definition would be, we will look at what is the input capacitance of all of these designs, all of these gates, and we'll sum all of that up and we have some load capacitance. So CL by the C in for this inverter gives us the definition for fan out. Now the other definition will simply tell you that the fan out is equal to 3 because it is simply driving 3 other logic gates. Now both these definitions will match if a particular gate is driving similar gates. So now if you hear the term fan out in some discussion, and if that fan out number is very critical in your design, please make sure both of you are using the same definition for fan out. Okay, so now we know how to calculate all of these parameters. Then when we cascade multiple such gates, we can calculate the total delay of this given by capital D. This will be equal to summation of all the DIs, the delay of the individual gates. And this is equal to the path parasitic delay plus capital H. Is this correct? So what it should have been is, this is summation of DI, right? So it should be summation of all the PIs plus summation of all the GI into HI, right? So this is capital P plus this remains as it is. So basically it is summation of all the FIs, okay? But given a circuit like this, now you know what is the minimum delay possible. So this is the actual delay present. The minimum delay possible will be equal to P plus, this is N into F raised to 1 by F, where this F is the path effort given by the expression that you just mentioned, GH into B. And now you know how to resize the gates in this path such that you can go from whatever delay you have currently to the minimum delay that is possible. Okay, so if the number of stages N is fixed, what is the optimal F? Optimal stage effort? N is fixed. You don't have control over N. So then this is F raised to 1 by N. If N is not fixed, then the optimal stage effort is 4. Therefore, the number of stages required to achieve this optimal stage effort is given by log of F to the base 4. So you will first calculate N. This might not be a nice integer number, in which case you will approximate it to one of the closest integers, and then you can back calculate what is the F stage effort that you have achieved in your design. So now, let's say I take an inverter. This is sized at unity. And I am driving multiple other inverters. Let's say N inverters. Maybe I should use a different variable. M inverters. All of these are size-state unity, right? Now, if I want to achieve the optimal stage effort, what should be the value for M? So I'm looking at the stage effort for this inverter. It is driving M other inverters. If we have to achieve optimal stage effort for this inverter, what should be the value of M? M should be equal to 1. Right. So let us calculate the stage effort. This is equal to G into H. Right. So what is G for this inverter? 1. What is H? So this will be M into 3C divided by 3C. That will give you M. And what should this be equal to? Should be equal to 4. So this is basically 1 into M should be equal to 4. So M should be equal to 4. Okay. So to achieve optimal stage effort, this is the configuration you will have when an inverter is driving 4 other inverters. Now this inverter is now called as the fan out of 4 inverter. So this inverter basically has a fan out of 4. So it's called as a fan out of 4 inverter. It is, so in short, it is called as FO4 inverter. So why this is important is fan out of 4 inverter delay is a metric that is sometimes used to compare different technology nodes. So you look at the FO4 inverter delay in, let's say, 130 nanometer, 28 nanometer, etc., to quickly compare which technology node is faster. We would expect the lower technology node to be faster, but how better it is, we will quickly compare by comparing the FO4 delays. And in this case, what is the D minimum possible? So when N is not fixed, we said that F optimal is equal to 4. And then you can calculate N from it. What would be the D minimum? Capital P. So this is the P for the new path, including all the inverters or buffers that you have added. Plus 4 times. So 4 times N is basically. So one minor problem in doing this is, so I'm asking you what would be the minimum delay possible. For this particular case, N is not fixed. So you know that the optimal stage effort is 4. Then you back calculate N. Then I got the answer that D minimum will be equal to P plus 4N. Is this right? Why is it not right? So parasitic delay, let's assume that this is the new parasitic delay. You have included the, so let me write it as summation of Pi, where I goes from 1 to the end that you have chosen. Sorry? Right. So if you decrease the stage, your N changes. So if you have changed N, you are calculating it for the new N now. Right. Yeah, you were saying something. So are you talking about this diagram? So this is a different discussion. Here the delay is calculated for this inverter. Right. So this expression is correct if your N exactly matches with it. But like I said, you will not get an integer N here. So you would approximate it to one of the nearest numbers. So the right expression to apply here is N times F raised to 1 by N. Where ideally, if you were able to get a N as an integer number, this would have simplified down to 4. Okay. Any questions so far? Okay. So then we still wanted to reduce the delay possible better than what we can achieve from here. And we figured out that the way to go about it is by trying and reduce the total path effort, which then we figured out can be done if we keep reducing the logical effort of the individual gates that we are dealing with. And this sort of reduction in the logical effort is possible when we know more information about the inputs. For example, the first thing that we talked about was reordering the inputs. That actually doesn't reduce the logical effort, but it at least allows you to reduce parasitic effort. Right? Now, the next thing is to use asymmetric gates. And then we said that we can also use skewed gates. So asymmetric gates gives preference for one input over the other. So one input's logical effort is going to increase. The logical effort of the other input is going to decrease. Skewed gates are going to give preference for one transition over the other. So you can either make the logical effort for pull down path better or that for the pull up path better. And you have a penalty in terms of the logical effort for the opposite path increasing. Okay. Now all of this still fall under the complementary static CMOS implementation. Right. And then we saw that. So this complementary static CMOS implementation is basically a pull-up network and a pull-down network, both of them connected to the same sets of input. Right. Then we said that to get even better improvement, we will replace the PUN with a load. And we chose that load to be an always on PMOS. And what is this called as? This is pseudo NMOS logic. So we calculated the transistor sizes for a unit inverter in pseudo NMOS logic. What were the sizes? So the PMOS was 2/4. Let's say this is A and this is Y. NMOS was at 5/4. And this sizing was chosen such that the available pull down current, pull down output current was same as that of a reference CMOS inverter. Yeah. So what you will have to do then is this will have to be doubled the size and this will also have to increase accordingly. So if you want to have, so the idea is if the minimum size is equal to 1, right, you will have to, you can maybe have two things in series so that the L is doubled, right? Or in this particular case, we were not very much worried about the pull-up current. So you can retain it as 1. So that sizing you can take care of once you know what is the actual minimum size available to you and what possibilities are available. Right. For now, let's just assume that this 2/4 is possible for calculations. Okay, now we calculated both the logical effort for pull up and pull down path for this inverter. Is there any confusion on that? Should I repeat the calculations? So alpha, which came out of the expression from BOL, I assumed as something, I think 2/5, and then the rest of the calculations came. Is the calculation for logical effort for pull up and pull down path clear in an inverter? So let us quickly do the calculation for NAND 2. This is in pseudo NMOS. So this was given as a homework. What answer did you get? What is GU and what is GD? Why don't you give it a try now? Can you tell me the size of PMOS here? This should be 2 by 4. Why? Because if the current coming from here is I, this has been designed to be 2 by 4 such that the current coming through a PMOS is also I. The pull-up output current is I. So to get the same pull-up output current, this also has to be sized at 2 by 4. Now the NMOS has been sized at 5 by 4 such that the pull-down output current available is I. Right? So in which case, what should be these sizes? So I hear the answer 5 by 8. Is this correct? 5 by 2. Okay. Any doubts on the sizing for the NAND? Okay, perfect. Then we need to calculate both GD and GU for this. So let us quickly calculate the GD. So I first have to look at what is the input capacitance. Now here both A and B are symmetrical. So whether I calculate the logical effort for A or B, it doesn't make any difference, right? Both of them are sized at the same. So the input capacitance is 5 by 2 into C divided by 3C. Why 3C? Because now I have to look at the inverter that has the same pull down current. So if this current is I, then this current also should be I. So that is sized at 1 and 2 because that is how we have designed this NAND. Therefore, you have 5 by 2C by 3C, which is equal to did we make a mistake? Fine. That's correct. Now, what about GU? Yeah. Numerator is so this is now a NAND, right? So this is my A, this is my B. I have to look at what is the total capacitance at A now, right? Or total capacitance at B. We look at one input at the time. So let this be GDA. GDA will be equal to GDB because both these transistors are identical, right? Now, what is the capacitance at the input A? That is equal to 5 by 2C, right? Now, if you had a pull-up network, which was also connected to the inputs A and B, then you will have CP plus CN, right? So in complementary static CMOS implementation, your NAND gate was like this. So for this, if I were drawing the logic gate and looking at the total capacitance connected to A, you will have a 2C from here because this is sized at 2 and another 2C from here, right? Therefore, the total capacitance here was equal to 4C, which was CP plus CN. Now here, CP is equal to 0, you have only CN because you don't have the input being connected to the pull-up network. Is this clear? Right. So what is GU? What is in the numerator? So numerator is still 5 by 2C. Now I have to figure out the inverter that I need to use for comparing with this. So again, you have a NAND gate. So you have to, for the logical effort, you have to look at the input capacitance divided by the input capacitance of the unit inverter that can provide the same output current. I am looking only at the input capacitance of the net. Now, even to get a pull up, you actually want your V to, you actually want your A to have a falling edge so that this node can pull it up. So when you have a transition at A, that is when you can still have either a rising edge or falling edge at the output. The rising edge is determined by the current strength of the PMOS. Falling edge is determined by the current strength of the pull down network. That's all. So which is why even for this, the input capacitance is 5/2C. So now I have to compare it with a reference CMOS inverter that has the same output pull-up current or same output charging current. So if the available output charging current here is I, we know that the same I is flowing through this PMOS. Is that clear? There is no other path, right? Because your pull-down network is now completely off. So what should be the size of the PMOS such that I get the same I here? It should be 2. What is the size here? This is 1/2. So a PMOS sized at 1/2 is providing the current I. So what should it be here? I need the same current I, therefore this should be 1/2. Clear? Now, if this is 1/2, what should be NMOS? 1/4. So the total capacitance at the input of this inverter is now 3/4C. So you get that in the denominator. So let's say I have a current I for discharging the capacitor. So you get this as 10/3. Okay. Just to make sure that you have understood the calculation, why don't you repeat the same exercise for NOR 3? Again in pseudo NMOS logic. So let's first sketch the NOR. What is the size of the PMOS? This is still at 2/4. Size of the NMOS? All of them at 5/4. Sorry. It will be same for any input. So your GU you should have obtained as 5/3 and GD should be equal to 5/12. So clearly the 5/3 you want to, okay. So let us so you are looking at this is a NOR gate, right? You are looking at the delay from one input to the output, right? So if a transition in this has to, because if the others are on, then so, and this is especially a pull down transition, right? So if the others are already on, for the pull up, correct. So all of them need to be off, right? Why? No, I'm not following the calculation. Why do you say that? So did you have an equivalent RC circuit in mind? So you're making that statement based on some assumptions, right? What does that mean? Meaning this node. But so you're talking about the, so something else is driving this NOR gate. So now if you think about having to drive all of these, then you're talking about the delay of the previous stage. This becomes the load for the previous stage. Right? Yeah. Right. So let me quickly solve this. So GU is what you wanted, right? So the input capacitance is still 5/4C. Now for this particular case, the reference inverter you have to use is this. Therefore, in the denominator, you will have 3/4C. So this will give you 5/3. Now, if you use an N input NOR, the values of GU and GD will remain the same. Now, this is different from complementary static CMOS implementation of NOR, where as your N increases, the logical effort of the NOR gate was increasing, right? It was related to N. Whereas here, you can go from any value of inputs to a very large value of input, and your logical effort is still remaining same. Okay, so that is, which tells you that if you had to use NOR gate, and if you wanted an optimal implementation in terms of delay, pseudo NMOS logic is a decent option to consider. Right? Okay. So now the problem with pseudo NMOS logic is that it has a static power consumption. So can you think of a way such that we still have the benefits of pseudo NMOS logic in terms of the delay, but we can get rid of static CMOS power, static power consumption? So let me take the example of the inverter. So when A is equal to 1, you will have a power current flowing from VDD to ground. What can you do such that you can get rid of this current flowing even when A is equal to 1? You want to connect up, but the moment you connect a PMOS on top, you are tampering with the benefits you are getting, right? So your suggestion is to have A connected like this. Is that the suggestion? So toggle this PMOS. That is in the right direction. Now let's say I have also given you A bar. Can you think of a differential implementation that will allow you to achieve what you just suggested? Somehow toggle the PMOS. And you have to toggle the PMOS when A is equal to 1. Like when A is equal to 1, you need to switch it off. How would you make it dependent on the output? We can use the differential configuration and so let us look at that solution, right? So let me take one more branch. Okay, let's say this is my Y. I'm connecting A bar here, and let me call this as Y bar. Okay, so now I'm going to connect the cross-couple these PMOSs. So just for aesthetic purposes, I will simply modify the circuit a little bit. So I will draw the PMOS gates inwards. So this is A, this is my Y. This is A bar, this is Y bar, and I connect the inputs to the PMOS as shown here. So let's start with a sample scenario. Let's say A is equal to 0, then A bar is equal to 1. right? If A is equal to 0, there is no current through this NMOS. You will have a current through this NMOS, and Y bar will settle to, will it settle to 0? It will settle to VOL. Now, if Y bar is VOL, and assuming we did a decent job for designing for a VOL, what comment can you make about this PMOS? This will be on, right? So you will have a current flow. Because this NMOS is off, Y is now going to settle to VDD. Now that Y has settled to VDD, this PMOS completely turns off. Once this completely turns off, now this NMOS can pull it all the way down to 0. Is this clear? How does this node charge to VDD? So let me call the transistors as, let's say this is M1 and this is M2, right? M1 is off, M2 is on, right? So you have a current. So if you wait for sufficient time, this will charge to VDD. What that time is will depend on the current available, the sizing of the PMOS and the current available. Why would it charge to VDD minus VTP? Which one? So let's call this as M3 and this is M4. You are saying M2. So M2 is VOL, we assume it to be a small value, which means this is on with some VSD, right? And the VSD is VOL, right? So it is always on, which means this node can now go all the way till VDD, till the VSD of the PMOS becomes 0. This is gate. And this is source, and this is, why is the drain of the PMOS? The source gate voltage is equal to VDD minus VOL, which is greater than mod VTP, which means M2 can never turn off. Its current can go to 0 when it is in linear region with VSD equal to 0. Okay. Is the idea clear to everyone? So the idea is quite elegant and actually simple, right? It's not complicated, but the name is slightly complicated. So this is called as DC VSL. It stands for differential cascade voltage switch logic. It has a big name, but the idea is actually quite simple and very nice. So what is the static power consumption now? So under steady state, all the outputs are settling nicely to 0 or VDD, and you have only the pull up or pull down path on in each of the branches. Okay, so we have constructed an inverter using DC VSL. Why don't you guys construct a NAND too using DC VSL? So of course, you can assume that the true value of the inputs as well as their complements are available. And in having to construct this, you will have to do pull down networks for both Y and Y bar. Let's say this is Y and Y bar, and we want Y to be equal to A dot B, the whole bar. So this is easy to implement. Now I need to implement y bar here, right? So y bar is a dot b, the whole bar. So this will give you a bar plus b bar. So what are the advantages of this method? The first thing is, of course, there is no static power. Which one? Right. Sorry. This is a bar plus b bar, the whole bar, right? Which is what I've implemented here. Thanks. Is this clear? So we anyways need to have the expression we want to implement in an inverting form. So we need to retain the bar at the top. Okay, so what are the advantages of this DC-VSL circuit? First step, of course, is that static power is equal to 0. Then compared to complementary CMOS circuit, we expect the logical effort to be lower because we have retained the same structure as the pseudo NMOS logic. It also gives you both the output and its complement. So if your application requires both the output and its complement, then this is something that you can think of, right? What are the disadvantages? Yeah, so area has now increased. And also you require both the input and its complement. Right? So if you are working with an application where the input and its complement is already available, right? And you anyways require output and its complement, then DC-VSL is something that you can consider, right? But let's say input and its complement is not available. Then to create its complement, you will have to use an inverter. Plus you are losing out on so much area for the DC-VSL implementation. So in using that inverter prior, you are introducing some delay and then you're losing out on more area in this. So maybe the advantages you get might not justify the penalty that you are paying. So depending on the application, you will have to take a call whether this circuit is suitable for you or not. Okay, any questions so far? We cannot. VOH is equal to? Yeah, understood. This is now ratioless. True, that is correct. Okay, so far we have been connecting our inputs to the gate of the transistor, right? What if we also start connecting our inputs to one of the other terminals of the transistor? That gives you the pass transistor logic. So this brings us to another style of combinational circuit design called as pass transistor logic. So now let me give you a circuit and you can tell me what this circuit is implementing. What is the expression for Y? A plus B, A dot B. Right? Now, if you had to implement this AND gate using complementary static CMOS logic, how many transistors would you require? 6, right? 4 to implement the NAND and 2 more to invert it, right? And here we have implemented this using only 2 transistors. But what is there any problem with this implementation? Correct. So if A is equal to 1 and B is equal to 1, basically both A and B are at VDD, what is the output? This will only go till VDD minus VTN. So what can we do to solve this issue? So the problem is happening because the NMOS is not good at transferring logic 1, right? So I can use a PMOS, but then I'll have a problem transferring logic 0. So use both. So that brings us to the first solution to get rid of this problem of your output not being equal to VDD is to use a transmission gate. So a transmission gate is an NMOS and a PMOS connected in parallel like this. If I connect A here, what should I connect here? It has to be A bar because we want the switch to be on as a whole. So if the NMOS is on, the PMOS should also be on at the same time. And this is generally represented like this. You can think of bringing both the transistors close together. So this is what is generally represented. And this pass transistor implementation is especially useful in implementing multiplexers. So can you implement a 2:1 mux? Can you do a pass transistor implementation using transmission gates for this? So we want I1 to go through when S is equal to 0. This is S bar, this should be connected to S. And I2 to go through when S is equal to 1. Is this implementation clear? So now, at any point, only one of the paths is on. The other path is simply high impedance. Much like when you had a PUN and PDN in a static CMOS logic, you would have one of them under high impedance, completely floating and completely off and not driving the output, whereas the other would be driving the output either to VDD or ground. Same fashion, you can connect multiple branches like this, and only one of the branches will be actually driving the output. All the others will be off. All right. So now let's say I am driving this I1 with an inverter. If an inverter was driving any other complementary static CMOS gate or any other input which is connected to a gate, you can model its capacitance as some CL and then do the calculation for the delay of this inverter. How would you proceed if I wanted to calculate the delay of this inverter? So I'm asking you, how should you model the load provided by this multiplexer? So what is how do I go about modeling the CL? So sum of the parasitic capacitance at this node. Everybody agrees? Any other answers? Okay, let's say the load here is very high. Would that affect the delay of this inverter? Based on the answer you have just said, it shouldn't. If I'm looking only at the sum of the parasitics at this node. So this can be modeled as some equivalent resistor, right? The switch, when it is turned on, is offering some equivalent resistance, followed by whatever you are seeing at its output. So to that, you will add whatever is the parasitics here. And then depending on whether you are looking at the pull-up path, the rising edge or the falling edge, you will add the equivalent resistance. Let's say you're looking at the falling edge, then you will add R equivalent N. And then you have to calculate the delay. Is that clear? So if you want to compare two circuits, let's say two transmission gate-based implementations, I would recommend you include the driver also as part of your circuit, right? Put the same driver for both the gates and then look at the delay from the input of the driver to the output. If you assume an ideal source here and start driving it versus having a driver here and assuming an ideal source here, both of them are going to give you very different. All right. So one solution to pull up the output back to VDD is to use a transmission gate. Is there anything else that we can do? So let me bring the example of the NAND again. So this is A, B, A bar and ground. So when A is equal to 1, B is equal to 1, this node doesn't reach all the way till VDD. What else can I do to bring it back to VDD? I use a buffer. Okay, let's say I use an inverter. But this node is still not coming back till VDD, right? So I can bring it. Right? So if this is now at VDD minus VT, yeah, this one will turn on. This node will get pulled down to 0, because of which this is now on and it will bring it all the way up to VDD. Okay. So now let me get back to the solution you gave earlier, right? Use a buffer or basically use an inverter, right? Now this node is at a clearly defined logic level. Why are we so worried about this VDD minus VT here? When you cascade, it can decrease. But also, this node is now more sensitive to the noise. Even if some noise gets coupled here, it can easily go below the VIH of the next inverter. So ideally, we would like all our voltages to go to VDD or ground. Now, can you implement? So this is called as restoring logic. Right? Now, can you implement a 4:1 mux using the restoring logic? Which two transistors? So you can either use transmission gates or you don't have to use transmission gates and use a restoring logic. Which is a... So let us analyze that. So what we pointed out was that, let's say this is MP1 and this is MN1, right? And we are talking about the case where your output now needs to go from VDD all the way down to 0. Okay, so let's start with the assumption that this node is at VDD, right? And let's say this path has turned off and this path has turned on. Now you have two devices connected to this node. One is this PMOS trying to pull it up to VDD. The other is this NMOS trying to pull it all the way down to 0. So there is a contention between two paths. Now, if your PMOS was stronger, this voltage is going to, it will be closer to VDD, right? It will settle down to some voltage which is closer to VDD, because of which this will still be closer to 0. So this circuit would still be active and you will not be able to bring it all the way down to 0. But if you size your MN1 such that this has a higher drive strength, then this voltage will settle to somewhere closer to 0, because of which this will go till VDD and then this path gets turned off. So initially it will settle down to somewhere closer to 0, let's say some sort of VOL value. And then once this goes to a high value and this turns off, then MN1 can pull it all the way down to 0. So did you construct the 4:1 mux? So now you will have S1 and S0 connected here. I1, I2, I3, and I4. Quickly tell me what I should connect to these gates. So this is S1 bar, S0 bar, S1 bar, S0, S1, S0 bar, S1, and S0. So now if I ask you to make 8:1 mux, how many switches will you have in series? 3. As I keep increasing the inputs to the multiplexer, you will have to keep increasing the number of switches here. Is that okay, or is there a problem with delay? Yeah, so series resistance is increasing, but more than that, you have some parasitic capacitance at this node, right? So now your resistor network is going to look like this. And from Elmore delay model, when we did the calculation, we know that as the number of resistors is increasing, let's say it is increasing by some value n, your delay is going to quadratically increase. Right? So it is not really nice to have so many transistors in series here. In such a case, what can you do? So let's say this is at VDD. What would be the voltage here? This is VDD minus VTN. What is the voltage here? This is also at VDD minus VTN. Right? But if I keep adding restoring logics at all these modules, then the circuit is also going to get a lot bigger. So in this case, usually the restoring logic is added at the output. Why would it be VDD minus 2 VTN? So in making this assumption, I'm saying that the gate is at VDD. Okay. So think of what you can do. Let's say I want to implement a 64:1 mux, right? In which case I will need to have a lot of transistors in series. Think of what you can do to avoid this problem. Okay, thank you.